We are getting straight into the meat of it today with a massive paper titled A Very Big Video Reasoning Suite, or VBVR for short. This comes from a really huge consortium of researchers. We're talking UC Berkeley, NTU, Northeastern, UCSD, and like a dozen others. It is a major heavy hitter.
It really is. And to just give you the 1-minute abstract right up front before we unpack the technical details, this paper is tackling the single biggest bottleneck in video generation right now. Because we have models like Sora and Veo that can generate these beautiful cinematic videos, but they fail spectacularly at physical and spatial reasoning. They don't truly understand the world. They mimic how it looks.
Right, the pretty but dumb problem.
Exactly. So the solution these researchers are proposing is VBVR. It is a data set that is 1,000 times larger than any existing alternative for video reasoning. We're talking over 1 million generated video clips and over 2 million images across 200 specific tasks. And the key finding here is that when you train on this massive data set, you get what they call emergent generalization. The models stop just memorizing pixels and start to actually, understand physics and logic.
1,000 times larger is just a serious scale up. And for the ML engineers listening, this isn't just a dataset release. It's a proposal for a data factory approach to solving the reasoning gap.
Precisely. It's moving from curation to industrial generation.
So let's back up a bit and define the problem space. Because I think most people look at a Sora 2 video or a Kling 2.6 generation and think, wow, we solved it. It looks like a movie. But you're saying that visual realism is kind of a magic trick.
It is a very impressive magic trick. But yeah, if you look at the current state of the art, Sora 2, Veo 3.1, Kling 2.6, they are visually stunning. But the paper argues that if you ask them to maintain a spatiotemporally consistent environment, they often just fall apart.
Spatiotemporally consistent. That's the technical term for things shouldn't vanish into thin air, right?
Basically, yeah. Do things stay where they're supposed to be? Do they move in a way that implies mass and momentum? Because text models, like the LLMs we use for coding, they've conquered logic. They can write code, they solve math. But video models are currently just creative tools. They are dreaming, they're not reasoning.
So if I ask a video model to show a ball rolling behind a box, sometimes the ball just teleports to the wall.
Exactly, or it turns into a cat. The problem has been that previous benchmarks to test this were tiny. Things like Video Zero Shot or MMGR, they only had a few thousand samples. They were great for grading models.
Like a pop quiz.
Right, like a pop quiz, but you couldn't train on them. They were evaluation heavy. So VBVR is trying to flip that entirely. They want to move from optimizing for visual quality to optimizing for grounded intelligence. Continuity, interaction, causality.
Grounded intelligence.
Yeah.
I really like that. It's like sending the AI to engineering school instead of art school.
That is a great analogy. And to build that curriculum, the team actually went back to philosophy. They grounded their entire taxonomy in Aristotle and Kant.
Wait, we're doing AI research based on Immanuel Kant now.
We are. They looked at the faculties of the mind. They broke down video reasoning into 5 specific pillars to make sure they weren't just making random videos, but actually testing distinct cognitive skills.
Okay, let's run through these 5 pillars because this taxonomy seems really crucial for anyone trying to build a world model. What are we actually testing here?
First, you have perception. This is the most basic level. Can the model extract structure? Can it see edges, colors, shapes? An example task here is identifying a pentagon hidden among other shapes.
Okay, simple enough. I see a shape, I know what it is. That seems like table stakes for a vision model.
You'd think so, but accurate geometry is actually harder than texture. The next pillar is transformation. This relates to manipulating mental representations. Think of the game Tetris, or mental rotation. One of the tasks in the suite involves showing L-shaped pipes at different angles, and the model has to mentally rotate them to form a closed square loop.
So it's not just seeing the pipe, it has to imagine the pipe moving and then predict the end state.
Exactly. It has to simulate that rotation. Then you have spatiality. This is about geometric relationships and navigation. A classic example here is a maze. Can the model move an agent from a green start point to a red flag without passing through the walls?
That seems incredibly hard for a video model because it has to remember where the walls are frame by frame. Like if it forgets the wall exists in frame 50, it walks right through it.
Yeah, that is the long horizon problem. The 4th pillar is abstraction. This is about finding rules. Think of Raven's matrices, those IQ test patterns where you have to guess the next image in the sequence.
Right, pattern recognition, like circle, square, circle, square.
But visual, yeah. And finally, the 5th pillar is knowledge. This is about propositional truths in physics. They have tasks simulating fluid dynamics, like communicating vessels, where water levels equalize across connected tubes, or gravity simulations, even traffic light logic.
Traffic lights.
Yeah. Does the car go on green and stop on red? That is knowledge about how the world works. It's a rule-based constraint that isn't strictly physics, but is strictly logic.
So we have these 5 pillars covering everything from what shape is that to how does fluid flow. But you mentioned this is a data set of 1 million clips.
Yeah.
They didn't animate these by hand, obviously.
Yeah. And crucially, they didn't scrape YouTube either. And this is a really important point for the engineers listening. Scraping YouTube is highly problematic for reasoning because you don't have the ground truth.
Right. If I watch a video of a cat jumping, I see the pixels, but I don't have a mathematical record of the cat's trajectory.
Exactly. You don't have a coordinate system telling you exactly where every pixel should be at any given millisecond. So they built a data factory.
A data factory. I love the sound of that.
They call it a data spring architecture. It uses procedural generation. They literally wrote over 200 parameterized generators in Python code.
So they wrote code that writes video.
They wrote code that generates the scenario for the video. They deploy these on AWS Lambda workers.
Oh, so thousands of little serverless functions running in the cloud.
Yeah, writing data directly to S3 storage. And because it's code, they can scale it infinitely. Right now it's at 1 million training samples, but they could push a button and make it 10 million.
And because it's code, they know the right answer. They know that at frame 10, the ball is at coordinate X, Y.
Exactly. And that allows for strict constraint checking. They have 3 big rules for every video generated to ensure high quality. First, information sufficiency. All the cues to solve the puzzle must be in the first frame or the prompt. No guessing games.
Fair. You can't solve a puzzle if pieces are missing.
Second is video dependency. The task must require time to pass. You can't just solve it by looking at a single static image. The solution is the motion itself. And third, deterministic solvability. There must be a verifiable, objective, right answer.
Which sets it apart from creative video generation, where good is totally subjective. Like if I ask for a cool explosion, any explosion is fine. But if I ask for a specific fluid dynamic simulation, there's only one right way the water flows.
Precisely. And they were very careful with how they split the data. They have 100 tasks for training and 100 completely different tasks for testing. And crucially, the test set includes out-of-domain or ODE tasks.
ODE. So testing the model on things it has literally never seen before.
Yes. It's the difference between memorizing the answers to a math test and actually learning the principles of mathematics so you can solve brand new problems. They want to test generalization, not memorization.
This brings us to the evaluation side of things. You mentioned earlier that benchmarks like this usually rely on VLM as a judge. Can you explain what that is and why the VBVR team completely rejected it?
Sure. So VLM stands for Vision Language Model. The trend recently has been to use a model like GPT-4V or Gemini to look at a video generated by another model and grade it, basically asking the AI, did this video look correct?
So AI grading AI.
Yeah. And the paper argues this is a terrible idea for reasoning. VLMs are stochastic, they are random, they hallucinate, they might say a video is corrupt when it isn't just because it looks pretty, or they might fail a perfectly correct video because of some weird pixel artifact.
So how does VBVR grade the models if they refuse to use an AI judge?
They use rule-based verifiable scores. Because the data is procedurally generated via that Python code we talked about, the system knows exactly where the object is supposed to be at frame 50. They measure 3 specific metrics. TC, which is task completion, did the agent reach the goal? RL, reasoning logic, did it follow the rules, like not walking through a wall? And VQ, visual quality, did the object stay the same color and shape?
That sounds much more rigorous. It's essentially binary. You passed or you failed.
It is. And to prove it works, they validated these automated scores against actual human preferences. They found a Spearman's correlation of over 0.9. That means the automated system agrees with human judges almost perfectly.
And how do humans score on these tasks, just as a baseline?
That is the human ceiling. Humans score about 97.4% on these tasks. We are naturally very good at intuitive physics, but as we will see, the models, they are not there yet.
Okay, let's get to the results then. They have the factory, they have the rigorous test. What happened when they actually trained a model on this?
They ran a scaling study using an open source model called WAN 2.2. They took this model and trained it on increasing amounts of VBVR data from small batches all the way up to the full million clips.
And did it get smarter?
It did. And this is the real aha moment of the paper. Performance improved on both the in-domain tasks, the ones it practiced, and the out-of-domain tasks, the ones it hadn't seen. The in-domain score went from roughly 0.41 to 0.76, but the out-of-domain score jumped from 0.33 to 0.61.
So it actually learned physics. It didn't just memorize the specific videos.
It strongly suggests emergent generalization. The model isn't just memorizing specific pixel patterns, it is learning underlying rules of motion and logic that transfer to new, unseen situations. It learned how things move, not just that they move.
That is huge. But I was looking at the charts in the paper. Did it keep going up forever?
No, and this is the reality check. Performance eventually plateaued. There is a persistent gap between the model's performance around 61% on owed tasks and that human ceiling of 97%. Data scaling alone didn't close it.
So throwing more data at the problem helped, but it hit a hard wall.
It suggests that current architectures, the actual way these diffusion transformers are built, might have fundamental limitations. They might need a new way of thinking, not just more training data. They might need explicit memory modules or causal reasoning blocks built in.
Was there anything the model did that was surprising, though? Like, did it come up with its own solutions to things?
There was one fascinating qualitative insight. They highlight task 049. This was an unseen task involving filling in grid cells to complete a pattern. When the model encountered this, instead of editing the cells one by one like a computer program might or like a human might draw it,
Right.
it developed a unique fade-in strategy.
The fade-in strategy.
Yeah, it smoothly faded the colors into the grid cells over several frames to solve the pattern. It developed a stable, self-chosen policy for solving a novel problem that wasn't explicitly taught. It's a glimpse of the model developing its own internal how-to guide for interacting with the world.
That is incredibly cool and honestly slightly eerie. It's finding efficient paths we didn't teach it. So looking at the leaderboard overall, who is winning? Is Google winning? OpenAI.
They tested the big proprietary models VO 3.1 from Google, Sora 2 from OpenAI. They perform well, but they are beatable. The specialized open source model trained on VBVR data actually outperformed them on these specific reasoning tasks.
That makes sense, I suppose. Specialization beats generalization. But it also shows that the big models haven't solved physics yet.
Far from it. The gap is still very real. Even the best models struggle with long horizon reasoning, basically keeping track of things over a long video.
Now, here is where it gets really interesting for me. The paper dives into neuroscience. I definitely didn't expect to see brain scans mentioned in a video generation paper.
This is my favorite part. They looked at the correlation matrix between those 5 pillars we discussed earlier. They wanted to see if a model is good at one thing, what else is it naturally good at?
And what did they find?
They found a really strong positive coupling between knowledge and spatiality. The correlation was 0.461, which is significant.
So models that are good at navigating mazes are also good at understanding facts in physics.
Exactly. And this mirrors human neuroscience perfectly. In the human brain, we have the hippocampus. It's famous for place cells and grid cells. It's our internal GPS. But that same part of the brain is crucial for abstract concepts and memories.
Oh, like the memory palace technique.
Yes. When you memorize a speech by imagining walking through your house, you are hacking this exact link. Our ability to navigate space is deeply linked to how we structure abstract concepts. The paper suggests that these video models are developing a similar internal structure. To understand knowledge, they actually need to understand space.
That is profound. It implies that you can't just have a brain in a jar that knows facts like an LLM. You need a brain that knows where it is.
It completely validates the idea of embodied AI. Interestingly, the transformation pillar, that mental rotation stuff, didn't correlate well with the others. It seems to be a distinct module. Just like some humans are great at math but have absolutely no sense of direction, or vice versa, the models are developing distinct cognitive profiles.
So we have a massive data set, we have proof that scaling works but hits a limit, and we have this wild connection to how the human brain organizes information.
That sums it up perfectly. VBVR proves we can train video models to reason, not just hallucinate pretty pictures.
Yeah.
But it also proves we need massive, procedural, incredibly clean data to do it.
And for the engineers listening today, the real takeaway seems to be stop scraping YouTube. Build a data factory.
The future is controllability first. If you are building world models, you need to look at procedural data generation to teach causality. You need to verify the pixels before you train on them.
I want to leave you, the listener, with a thought here. If spatial navigation and conceptual knowledge are so tightly linked, both in our biological brains and now seemingly in these silicon brains, are we approaching a point where we stop training language models and start training navigation models to achieve general intelligence?
That is the multi-billion-dollar question. If reasoning is fundamentally grounded in space, then text might just not be enough. The path to AGI might require models that can move, even if it's just inside a simulation.
A huge thank you to the team behind VBVR for releasing this work. If you want to dig into the data yourself, you can find it at video-reason.com. It is open for the community, and the visualizations are definitely worth the click.
It is an absolute goldmine. Highly recommend checking it out.
Thanks for tuning in to this deep dive on AI Paper Podcasts. We will catch you on the next one.